everyone, Andrew Turner here with Algebra 1's KCS at Home Summer Edition, and this is about polynomials. This is the fourth section that we're going to be doing for our summer edition of Algebra 1. So again, email me, andrew.turner@knoxschools.org over the summer if you have any questions regarding any of the content that's been assigned in your packet. So the first thing we're going to talk about is polynomial expressions, and I think even before we talk about those, I think we'll talk a little bit about where we've kind of gone. When we first talk about numbers in algebra and variables and all that, it's important to understand a few classifications. First, we have the word constant. And a constant is any number, for example, 2 or -4 or -24. These are all, none of them have variables, and so they, when you graph a constant, kind of like in the other video when I graphed 2000 to see when that exponential function reached 2000 bacteria, it's just kind of a horizontal line showing you where that output would be, whatever that number is. Well, next you learn about linear. And linear is anything that has x to the first power. So x, 2x, -2x, anything that's just got x to the first power we call linear. And linear could be a positive sloped line or a negative sloped line, but in general it's only going one direction. And constants are kind of going one direction, but in a sense I kind of think of this as kind of you have like a zero slope, just kind of like you have 0 x's. There's no x's in the problem. Well, then next we talk a little bit about quadratic, and anything that's quadratic is when you're talking about x squared. Maybe it's 3x squared or -12x squared. Not sure, but as long as it's got x squared as the largest exponent in the problem, you're going to see a two-directional graph. It goes down and then up, okay? Or maybe it goes up and then down, but it kind of creates this two-directional graph because the exponent's a 2. So I'm really kind of showing you a lot about Algebra 2 and some calculus ideas I wish I had known when I was in Algebra 1. Really helped me understand it, I think, when I got older, so I wish I had known it when I was younger. The next one you may know is cubic, x to the third. Or maybe it's 2x to the third, or -21x to the third. But a cubic has 3 directions. It goes up, back down, and then up again. Or maybe it goes down and then up and then down. But again, it's got 3 directions. And so all of these ideas just continue to step up, like x to the 4th. It's kind of like a quadratic, but it has 4 movements. Or x to the 5th, except it has 5 moves. 1, 2, 3, 4, 5. Okay? And so there's a lot of similarities between odd and even powers here, and this can really open up a lot of conversations about what we call polynomials. Polynomials are different variables with different exponents that create different models for different ideas. And so sometimes you may want to add or subtract polynomials, and a lot of times you're looking for what we call like terms. For example, 2x plus 3x is 5x, or 2x squared plus 3x squared is 5x squared. And same thing if you were subtracting, 12x minus 10x would be 2x. And the powers aren't changing when you group something. 1 marker plus 1 marker is 2 markers. The item doesn't change because you add or even subtract. And so if you'll notice with these, it's like you're looking for the terms that go together so that you can -8, -12, -20, and then keep the power the same. So you may ask yourself, well, why would you ever want to do that? Well, sometimes you have scenarios, for example, let's say you were modeling different types of species. You had a certain type of parrot that was endangered, an orange-bellied parrot, and then a yellow-headed parrot. And so one of them is modeled by a linear function. Their population is decreasing over time. And the other one had a population that was more quadratic. It was more going down, but then over time that species recovered. And if you really think about it, they're both parrots. They're different types of parrots. And so we may want to take these 2 models that model each species population separately, and we may want to add them together to know how many total parrots we have, no matter which species it is. And so I'm looking to add those 2 given expressions together. 4x squared doesn't have a like term with the other equation, so I'm just going to say, well, 0 plus 4x squared is 4x squared. And if we continue, okay, negative 18 plus negative 5, that'd be negative 23x. And then 120 plus 25, that'd be 145. And then this would represent the total population based on your year from the study's beginning of how many total parents that you would have in general. So we're going to step away from context for a minute and just kind of talk about general ways to multiply polynomials outside of a story or a word problem. So let's say you wanted to multiply 3x minus 2 times 12x plus 7. So I'm going to show you a little box method that a lot of teachers show. I'm going to say, okay, we've got 3x minus 2, and we also have 12x and positive 7 here. And so this little dot represents our multiplication concept. So let's go through and let's just multiply within the grid everything that we see. So if I think about, 12x times 3x, 12 times 3 would be 36. X times x makes x squared. Well, then let's multiply. Well, 12x could multiply with negative 2. 12 times negative 2 would be negative 24, but you also have the x that was a part of that multiplication as well. So now let's slide down to the 7 and let's multiply it to the 3x. 7 times 3x would be 21x. And if I multiply 7 times negative 2, that would be negative 14. And so now I'm really kind of wanting to represent this as a simplified answer. And so I'm looking for things that can kind of combine or add together. And so the first thing I notice is that this is quadratic. 36x squared is not going to change. However, I could combine 21x and negative 24x. You could think of us adding together, or you could think of 21x minus 24x. Well, that would be negative 3x. You would combine those like terms together. And then you have this constant at the end of minus 14 that doesn't really change. And so some people don't really use the model like that. Some don't draw the box. They just use what's like double distribution, 3x times 12x, 36x squared. 3x times 7, 21x. Negative 2 times 12x, negative 24x. Negative 2 times 7, negative 14. And then you can simplify any terms that need to go together in order to, get your final answer after you have combined like terms. Okay? So that is when we want to talk about multiplying polynomials together. Let's talk about the complete opposite of that, which is this entire world of what we call factoring. So we're going to start with talking about greatest common factor of polynomials. So when we think about the word factor, if I said, what are the factors of 12? Well, you could say, 2 times 6 would be 12. Well, then, 6, that could be, 2 times 3. So what I just made is what's called a prime factorization tree. All the factors that go into 12 can be broken down. You have 2, 2, and 3. You multiply those together, you get 12. And you can think about all the different pairs that give you 12. 1 times 12, 2 times 6. Or you could think of like 2 times 4 would be, 2 times 2 is 4, and 4 times 3 would be 12. So these are all factors of 12. And if we're looking for the greatest common factor, it means you're talking about multiple constants that need to be considered, and which number below them would divide into every single one of them. For example, you have 3, 6, and 12. All of these numbers have a greatest common factor of 3. And that's because 3 is 3 times 1, 6 would be 3 times 2, and 12 would be 3 times 4. So 3 is the common factor, and it's actually the greatest common number that you can divide evenly into all 3 values. So similar to distribution, it's like I'm setting up what would have been distributed. I'm just dividing out what they have in common. I'm going to divide all of these by 3. So like I said, 3 divides by 3, I've got 1, and then the x squared. Now, a lot of times mathematicians won't write the 1. It's kind of an invisible understood 1. So I'm just going to put x squared there. I've got a plus, but not 6x. 6 divided by 3 is 2x. or 12 divided by 3 would be positive 4. And so now, if I were to distribute 3 to all of these values in the parenthesis, I would have exactly what I started with. And this allows us to do more simplification later in Algebra 2 when you take out a common value that has beefed all the numbers up to be larger than they need to be. Well, maybe I can divide a common factor out, like 3 in this case, to make the numbers a lot smaller, and maybe the problem will simplify a little bit. Now, let's talk about it when they have variables in common as well. So, when I'm looking at this problem, checking my time, 4, 8, and 6. 4 would be 2 times 2. Sorry, I didn't mean to do 2 commas there. 2 times 2, 8, or it's really negative 8. That would be 2 times negative 4. And then 6, well, that would be 2 times 3. So really thinking about all the numbers that would multiply or divide to be these values, and you can kind of think about what number below all of them they have in common. Well, really, they have other things in common. The first one has a squared, the middle one has an a, and the second one has a. So really, it's like they all have one a in common. Okay. They all have an a in common. Now the first one has an extra a, kind of like it has an extra 2. And the middle one and the last one, they each had one a each, so they didn't really have any extra a's in that sense. When I'm looking at the b's, the first one has a b, the second one has 2 b's, and the last one has a b. So really they all have up to 1 in common. So again, I give each of them a b. They all have in common. But the middle one had an extra b that was kind of like the negative 4 in that sense. Got to make sure that we keep everything there. So what do they all have in common? They all have 2 in common. They all have up to an a in common. And they have up to a b in common. Now, none of them have more than that in common. For example, I can't take 2 b's out of each one, because certain ones don't have 2 to take. And when I say take, I'm more thinking about division here. So 4 divided by 2 would be 2. But when we go to divide out a variable, we got to remember our power rules. A squared divided by a, I'm going to subtract those, 2 minus 1, and that leaves a 1 for my power. So if you were to multiply these together, 2ab times 2a, that produces 4a squared b, which is the exact first term that I have, but I have reduced it all by what's called the greatest common factor. Let's keep that going. The second one, if I divide negative 8 by 2, it leaves you with a negative 4. I've already taken an a out. I've already taken a b out, but that second term has an extra b that I need to take into account. So again, let me show you what I'm doing. I'm dividing that second position by what I said was the greatest common factor. Negative 8 divided by 2, negative 4. The a's cancel out. 1 minus 1 is 0. But for the b's, 2 minus 1, I have an extra 1 left there. Always check with multiplication. 2 times negative 4 is negative 8. A doesn't have a like term, but b and b makes b squared, and that's the exact term that you had in the middle. So the last one, let's divide 6ab by 2ab. And so 6 divided by 2 is 3. But for this one, the a's cancel, the b's cancel. We don't really need any a, b's in the parenthesis with 3, and that's because when you distribute, you'll get exactly what you need. You'll get that 6ab out in the end. So maybe I'll do one more example. 10x to the third plus 20x to the fourth plus 30x. So if I'm looking at the constants 10, 20, and 30, they're all divisible by 10. In terms of x's that they have in common, they have up to 1 in common. Really locking in on this last one, it only has 1 to give. Maybe the other ones have extras. That has 2 extra. This one has 3 extra. But what they have in common is just one of these x's. So wrapping this up, 10 divided by 10, 1. Subtract the powers, you get x squared. This will be 2x to the third, leaving what's left over there. And then for this one, it's just plus 3. So I'll see you in part 2 for polynomials.